just a brief recap of what happened last week. We um, just just right. So please, the students in the DL mode, kindly confirm if you can see my screen and the lecture slides. Okay, okay. So, right. Before going forward with our today's content, today's topic, network core, which is topic 1.3 in KNR. Right, right. It's mentioned right across the topic, and usually in the next few weeks, while we are trying to cover this basic networking material, we will follow the book Ross and Ross as a textbook, and the topic associated topic will be mentioned uh, just like this 1.3 Ross and Ross, 6th or 7th edition. This is our today's topic, network core, in which we will discuss switching, circuit switching and packet switching. But before going to that topic, just quickly reminding you guys what happened, a brief recap of for those of you who joined in this week, um, that we had a course introduction, okay? And I told you guys that this course will be heavy on layer 2 and layer 3 of networking of the internet protocol stack. So layer 2 is data link layer, and layer 3 is network layer, and this course will be basically heavy on those two layers. But having said that, we will cover I mean, we will touch at least the whole protocol stack, right from the application layer till the physical layer, okay? Because it is important so that everyone gets on the same page, because we have a very diverse audience in the MSIT, in the MSIT intake that we have usually over the years. And for that, I have chosen this particular book, Ross and Ross, and I have started discussing from chapter 1, which is the introduction. And in the chapter 1, our mandate is right in front. This will be the roadmap of chapter 1, in which we will discuss what is an internet. This was what we discussed in the last week. It was very generic discussion of internet. We all know about it. What are the nuts and bolts of internet? Like, we have different communication links, communication mediums, and then we have packet switches and routers and things like that. Okay, you can cover it up on or yourself. And if there is any query, any questions, I'll be available in office timings, and after that as well through email or whatever. Okay. Then we discuss the three segments of network. Okay, so the three segments of network are network edge, network access, and network core. And in the last week, we discussed the first two segments, which are network edge and network access. So just again, a very brief recap, very quickly. The edge of the network is basically all around the globe in the internet, the source and sink of the information. So all these devices where the information is either syncing or starting are the edge of the network. So usually the devices that we guys are using, our gadgets in our hand and in our pocket in front of us, or servers across the globe, or data centers. These are all the edge of the network. Okay? And then the access network is basically the last mile. So the technology that we are using from edge to get ourselves connected to the core of the network. And these technologies are usually ADSL, digital subscriber lines, 4G, 5G, Ethernet, and things like that. So this was the content that we covered during the last week of during the first week. Okay, and now we will start from the core of the network, which we will discuss today, and onwards we will go with this roadmap, which is right in front of us as the outline of chapter 1, Ross and Ross. Okay. Right, so let's continue with our today's topic, network core, circuit switching and packet switching 1.3. So, firstly, again, I just want to reconfirm my audibility from the students of DL mode. If there is any issue, please do write in the chat. Okay, do write in the chat, and I will visit the chat frequently. I mean, all the time. I will just keep an eye on the chat. If there is any chat message, I will, or you can turn on your mic and just speak. Okay, if you want to, if you have any question or comment on the topic that we are discussing. Okay, so in the core of the network, we are discussing two switching techniques: circuit switching and packet switching. Maybe you guys have already heard or learned about these two techniques, but just as I said, that the early part of the course may be a brief recap of many of you of your undergrad level networking course. Okay, so in circuit switching, basically we have an end-to-end resources allocated. Okay, for the entire entire session in which we want to communicate a source and a destination, two users basically. So, for example, in this diagram, you can see that we are dividing our link bandwidth, which is right here, okay, in 4 to 5 circuits, and all these circuits are of equal chunk, equal size, okay. So basically, it's like the perfect example of circuit switching is PSTN, Public Switch Telephone Network, right? Okay, in the PSTN, we I should, if I can, no, if I will switch to full screen, I will lose the this view, and I cannot see if there is a chat message. So, like the PSTN, the Public Switch Telephone Network, okay, and in this PSTN, basically we all have at our homes, we have a 4 kilohertz of circuit, dedicated bandwidth. Whenever we pick up our phone, we have this sort of circuit like performance. We have a guaranteed performance, okay, that we will have this particular latency and throughput throughout the whole session of the call that we will have. So um, this is a scenario when we have end-to-end resources dedicated, okay, and two type of division of bandwidth is possible. One is inside circuit switching. One is if we divide the bandwidth in terms of frequency, which is FDM, frequency division multiplexing, right here, okay, and another one is when we divide the bandwidth in terms of time, okay, so that is TDM, time division multiplexing, right here, okay. And let me give you guys example for both of them. So for example, I mean, the crux is that in circuit switching we have end-to-end resources dedicated, and we divide the bandwidth of the link into equal pieces or chunks, and we allocate one chunk or each chunk to one source destination pair for their entire communication period. Then the division of bandwidth in chunks is possible in two different ways. One is we divide the bandwidth in frequency, which is FDM right here, frequency division multiplexing, okay. And the other one is if we divide the bandwidth in time, which is yes, I'm just coming towards you. Frequency division multiplexing and then time division multiplexing, TDM, time division multiplexing. Yes, any question in the DL mode?
Sir, there is no question, but there is some sort of distortion or noise.
Okay, let me use. Also, your voice is very dim, very low in speaker. So let me use my earphone, and in case there is yeah, for the students in front of me. Okay. Now, am I uh, um, better? I mean, my voice is
Yes,
better now.
sir,
Is it
it's
more
fine.
audible? It's fine.
Yeah,
Okay.
it is fine. Earlier there was a noise of some type of airplane going
Okay. Okay.
over the
Right.
head.
Also, just to ease all of you, you can ask questions or have discussion with me in Urdu. Okay. And I will repeat your question for Abdullah. Okay. So there is no problem. I mean, only I am bound, not all of you. Okay. So this will make things easy for you guys, not because you are not fluent in English, but because we are, I am more comfortable in my own language, right? So, but obviously, in the presence of an international student, I cannot give lecture in Urdu, so that um, everyone can understand. Okay. Um, so all of you can, I have my earphone now, and I can hear you guys. I will repeat the question if there is any question from the DL mode. Okay. Right. So back to our topic. So here you can see that we have in the top diagram we have bandwidth of our link divided in chunks in terms of frequency. So we have 1, 2, 3, 4 chunks of bandwidth available. Okay. So we have somehow made 4 pieces of our bandwidth, 1, 2, 3, 4, and we can accommodate 4 users. Okay. So let's say the colors are there just to clarify the concept. Okay, so we have user one will get this share of bandwidth in the blue, and then green, and then yellow, and then red or pink, whatever, pink. One common example of FDM is the radio broadcasting. So we know that we have in our radio broadcasting systems we have the FM. We have different channels which are called FM 100, FM 101, some things like that. This is what happens. We have in here in Pakistan. So the same should be in Gambia as well. So in that is a perfect example of frequency division multiplexing, where we have a band of frequency from 89 megahertz to 108 megahertz, and then there are different radio channels which are communicating on their particular frequency, and all those channels have a dedicated chunk of frequency. So that's an example of a circuit switch network. Okay, radio broadcasting, in which each and every radio channel has a specific dedicated chunk of frequency which belong to that radio channel whenever it want to transmit, whether it transmit 24 hours or it has a specific transmission time, from 8 to 8 in the from morning to evening, whatever. Okay, this is an example of circuit switching. Another way is to divide the bandwidth in terms of time. In this way, what we do is that we have a specific, a specific frame like this. This is one frame, and then another frame like this, and then another frame like this. And in each frame, all the users will get a particular slot of time. Okay, so this is also circuit switching. The top diagram and the bottom diagram both are circuit switching, but in one example we are dividing the bandwidth in terms of frequency, in which all the users will have a particular chunk of frequency for the whole amount of time. And in the second example, we are dividing the bandwidth in terms of time, in which the user will have all the frequency, but only for the specific amount of time, and then it will wait for its own slot in the next frame. Okay. And the example of TDM is PSTN itself. Currently, the public switch telephone network is using TDM, not FDM. Previously, it was FDM. Now it is TDM. Now, one question come into our mind, that if we talk over the phone and we have our conversation in time slots like this, like the diagram mentioned in the bottom of the slide, then why we don't hear breakage in our conversation? The reason is that these time slots are so tightly spaced in the frame, one to the next frame, to the next frame, and up to so on, that the delay between the slots is not audible. The human ear can only sense any delay which is which is greater than 200 milliseconds. So TDM is fine, and in this particular scenario, the PSTN can also work on the TDM environment. Okay, so this is an example of the circuit switching. Now I will pose a question to all of you. Okay, the people who are in front of me and the people in the DL mod. I want to ask, before going to the next slide, that we have covered circuit switching, and I want to ask that consider or imagine our use of internet. Okay, and give me reasons that why this sort of bandwidth division, the one that happens in circuit switching, is not feasible for internet users. Why is like that? I mean, why? now we will move, obviously we will move towards packet switching. Okay, we studied at the start of the topic, we all know that we will study network core, and in the network core we will study circuit switching. There were only 2 slides in the circuit switching, and then we will study packet switching. Okay, and honestly, from now onward, for the rest of the whole course, we will just study packet switching. The internet is a packet switch network. Internet is a packet switch network. It is not a circuit switch network. So the whole course is, because it is all on the internet protocol stack, network switching and routing. And switching is layer 2, routing is layer 3. So basically what we will discuss is a packet switch network. So from these are only 2 slides in the course which were on the circuit switching. Okay. But before moving towards the packet switching, I want to ask you why we need packet switching for internet, why our use of internet is not suitable for this type of bandwidth division that we studied in the circuit switching. Anyone?
Because the internet is so much
Mm-hmm.
that you can, when it comes to packet switching itself, even though you're using TDM or FDM, but there are always the dedicated channel for you. But with the internet, whereby there are so many different devices communicating at any given time, you can't dedicate a channel to each and every device communicating with every other device.
Yes, so a very good reason that Abdullah gave. I mean, there are many reasons, and one of very and I have a reason in the chat as well, because circuit switching is not fast for internet. More than one paths available in packet switching. Yes, I mean, I will just repeat. This is correct, Jawad. What you have mentioned in the chat, this is correct. I will repeat what Abdullah has mentioned, and then I will show you guys all the reasons which are mentioned on the next slide. So the reason that Abdullah mentioned is that internet has so many devices. I mean, the global internet is a huge infrastructure, huge infrastructure. So it is very difficult for all the source destination pair to have a dedicated circuit allocated to them whenever they want to transmit. Okay, definitely, because I mean, if we have a source here at in Pakistan, in Islamabad, and a destination, let's say somewhere in California, the server of CNN.com. I mean, it is very hard to have a circuit maintained. In a PSTN, in a public switched telephone network, the whole infrastructure is owned by a single company. So Pakistan Telecommunication Limited, PTCL, owns the country infrastructure. So it is very easy for a PTCL to maintain a circuit from Islamabad to Karachi to have a phone call over that circuit. But beyond that, you will have to have discussion or SLAs, service level agreements with other parties outside your autonomy of your network of autonomy. But other than that, think about other reasons as well, which are very important. Before going to the next slide, think about your use of internet, how you use internet. The user usually use internet not in a circuit switched way, but in a packet switched way, which means that our use of internet is intermittent. Means we sometimes we want to connect, and I mean not intermittent. It is also intermittent. We come and go, but it is also of bursty nature. Bursty nature means that let's say I wrote on my browser www.cnn.com and I press enter. At that time, I generate a bus. I generate a bus because I want, at the back end, I generated an HTTP query, HTTP query that I want to get that web page. And in response, the server from somewhere around the world will transmit that web page to me. But after that, I will spend some seconds or maybe minutes viewing that web page, right? So the usual use of us as an internet user, our use is of bursty nature. And I mean, we generate burst of data, and then there are also silent period. So for even if we download a movie of 2 GB, but then after that, maybe we will view that movie. So we might not be using internet at that speed. We might not. So now if you move to the next slide, you will have all those reasons. Number one, inefficient. Okay, computer communications tends to be very bursty. For example, viewing a sequence of web page. So dedicated circuit cannot be used or shared in the period of silence. Okay, when we talk over the phone, we usually don't
put each other on hold for 30 minutes. The other party won't wait for us. They will just go. Okay. When we talk on phone, it's a continuous transmission. We talk for 2 minutes, 3 minutes, 5 minutes, 10 minutes, but it's continued, and then we hang up. We put the phone down. Okay. That's like it. So circuit switching is fine for that, but not for this sort of use. We use internet 24 hours a day, maybe. Okay. Apart from when we sleep. And a dedicated circuit for the whole period, it's not feasible. Okay. The second thing is fixed data rate. Now, when we use the phone, we always need the same amount of throughput from the public switch telephone network. We need 0 to 4 kilohertz of bandwidth, and we will talk fine with that. But in internet, sometime we use enormous amount of data rate. We are doing e-gaming. We are playing game on the internet. We use huge amount of bandwidth at the back end. Okay, throughput. And right now we are communicating over MS Teams. Significant amount of bandwidth is required for this as well. But if we are just viewing static web pages, or we are just, let's say, connecting with the remote server, we just need few kbs of throughput, and we are fine with that. And if someone seamlessly snatch our bandwidth without telling us, we won't be bothered, because right now the application we are using is not heavy on bandwidth. So second point, computer communicate at a very diverse rate. For example, viewing a video versus using telnet versus web browsing, these are all different rates. So fixed data rate is not useful. Okay. For a radio broadcasting, fixed data rate is fine, because the radio will always broadcast using the same data rate. Okay. And connection state maintenance, just like Abdullah mentioned, it is very difficult to maintain state because it will be a considerable overhead, because paths may be very, very long over the internet. Okay. So we will move towards our topic, which is packet switching. So circuit switching is not feasible. We have established this notion, and now we need something else. So what we do is like this. We will divide the
circuit switching से एक question है.
जी please.
सर ऊपर जो हमने डिस्कस किया TDM और FDM, दो मॉडल्स डिस्कस किए. जी इसमें आपने FDM की एग्जांपल दी थी कि FM FDM है. सर AM भी FDM नहीं है? उस पे भी डिफरेंट फ्रीक्वेंसीज के ऊपर चैनल्स आ रहे थे.
Yes, we had a question from मैंने मिस कर दिया.
Ali Amjad.
Ali Amjad. We have a question from Ali Amjad, and he is asking that from the circuit switching, where we gave example of frequency division multiplexing and time division multiplexing. So I quote radio broadcasting as an example, and radio broadcasting is FM, frequency modulated. So AM, he's saying that there are several radio stations who are also using AM, okay, amplitude modulation. So yes, AM is also an example of circuit switching, but the difference is that in AM, we will distinguish different radio stations on the basis of their amplitude, while in FM, we will distinguish different radio stations on the basis of their frequency. Both are circuit switching, okay. So these are physical layer phenomena. If we go deep, we will go into the EE domain. Then there are other things as well. So we have, phase as well, phase to recognize. So we have amplitude, we have frequency, and then we have phase as well. So if the amplitude and frequency both are same, we can still recognize different waveforms if they are of different phases. One is at 0 degree, one it has 90 degree to the other, and the other one is at 180 degree. That particular thing is called phase shift keying. Amplitude shift keying, phase shift keying, and frequency shift keying. But right now I am talking about the distribution of bandwidth, and these are categorized into these two techniques, which is FDM and TDM. Okay.
So AM is neither FDM nor TDM.
No, AM is neither FDM nor TDM. It's a separate technique which is based on amplitude. Okay. Good question. Thank you for that. Okay, let's move forward. So network core, packet switching. So okay, we have established a notion that circuit switching is not good for the internet. So for the internet, what we came up with, in mid 60s and late 60s, people gave this concept of packet switching, which is right here on the slide, which says host break application layer messages into packets. So the host will do what? I mean, it will break application layer messages into packets. The packets, all packets will be forwarded from one hop to the other, to the other, to the other, and in this way they will take a path towards the destination. Okay, and obviously then we need a whole protocol stack, and every layer will have its own responsibility. So application layer will break, and this is, I don't have to repeat it right now because it's a long discussion. This is what we will discuss during the whole course. So I mean, when the application layer break message, the transport layer will, you know, convert these messages into segments and then give it to IP layer, and which will, you know, put IP addresses as an header, and give it to data link layer, which will put MAC addresses, and then the packets will, you know, flow from one hop to the other till it reaches the destination. So each packet is kind of independent to another. So it means that on every packet we need to have the header information, and just like it's mentioned over here, each packet, when it will get its turn, will be transmitted at the full link capacity. Okay. So what new phenomena will come when we talk about packet switching? This was the slide which we discussed in the last lecture as well. Okay, and we discussed that because in packet switching, the application layer messages are divided into packets, and it's like I gave an example of a letter which is of 10 pages. Okay, and if we you know, separate all pages of a letter. I want to send letter to my friend, and if I separate all pages of the letter, then I will have to write on the envelope, on each envelope in which I put each and every one on 10 envelopes. So it's like application layer is dividing the whole message into number of packets, and on each packet it will have to write all the control information which is important and necessary to get that packet to the destination, just like my letter. Okay, so I have to write on the letter the source, destination, and everything else. So if that happens, then these new phenomena will come, like the store and forward. Okay, so store and forward, what is this? What is this phenomena? It says that when a packet is transmitted and it comes to the next hop, for example, here you can see it comes to the router. Okay, the router has to store the packet completely, because after storing the packet, the router will decapsulate headers, look into the headers, the IP address of the destination, and on the basis of that IP address will make a decision to forward it to a particular port. Although in this very simple example, there is only one outgoing port, but you can imagine that a router may have several outgoing ports, and it will have to decide that which outgoing port I will forward this particular packet. So, but the point is, it has to store the whole packet, then open up the content of the packet, read the content, and after reading those content, make a decision of forwarding that packet. So this store and forward phenomena will add some delay. This sort of delay is called transmission delay, and the transmission delay is denoted by the formula L by R, where L is the length of the packet and R is the rate of the link. Okay, so L is the length of the packet. Obviously, the transmission delay will be directly proportional on the length of the packet. If the length is more, the delay will be more, and inversely proportional on the rate of the link. So if the rate is high, then the router can push the packet quickly over the link. Okay, and by definition, if we just put it into pure words in English, by definition, how we can define the transmission delay? It is the delay required by a device or a router to push the entire packet from first bit till the last bit over the link. Okay, so the time required by the device to push the entire packet over the link is called the transmission delay. Okay. Not only that, in packet switching, there are even more phenomena which come. For example, after the transmission delay, we have another type of delay, which is queuing delay, because now that we don't have the medium shared, now that we don't have the medium or the links dedicated to the source destination pairs, and they are shared, and each packet is, you know, just forwarded, and then it's, you know, it's the luck of the packet whether it will have congestion at that time over on the routers, or it will have a free passage towards the destination. It's just the luck of the packet at that time, how many people are using the internet, right? Okay, so there is one more new phenomena that come. Okay, and that phenomena is called queuing delay. Okay, so queuing delay, when this phenomena happen, okay, this example illustrates perfectly the happening of queuing delay. So it's very simple. You can see that there are several hosts being shown here. Sorry, we have host A, B, C, D, and E, and we can see that this router over here, you know, it has two incoming links and one outgoing link, and we can see that the incoming links are of rate R, which is very high, and the outgoing links are of rate R, which is quite low compared to the incoming links. Okay, even if this is 100 megabit per second, if this rate is equal to this rate, even then the total incoming rate will be 2 times 100 megabit per second, 2R, and the outgoing rate is R. So this is the condition of happening of queuing delay, and it's written right over here. If the arrival rate in bits to the link exceeds the transmission rate of the link for a period of time, then what will happen? The packet will have to wait for the queue in the queue for a certain amount of time. It's like, you know, there are two roads which are of 2 lanes, and then they are merging into a junction, and the outgoing road is of 1 lane. So obviously there will be you know, a queue being made on that junction, because the cars will now have to wait, and they will be coming at higher speed, and then at the junction they will have to wait, and they will pass one by one, one by one, one by one. Just like Islamabad Express. Okay, so this phenomena is shown right here. Okay, so the condition is important. The condition is if the arrival rate in bits to the link exceeds to the transmission rate. Okay, you know, we can say, I can quickly switch to Urdu, you know, naturally, but I will come back. Okay, we can also say it like that, that the ingress rate is much greater or greater than the egress rate. Okay, it can be written something like that as well. Ingress rate is greater than the egress rate. Okay, incoming rate, outgoing rate, ingress rate, egress rate, all are the same jargons for the same meaning. Okay, so in that case, you know, queue will form just like here. Okay, and packet will have to be wait in the queue, and then on their own turn they will be transmitted. And there is another phenomena which can happen in packet switching. Obviously, if this situation persists for a longer period of time, then what will happen? The queue at the router is of a finite space. Okay, the router don't have you know, unlimited memory to hold up as many packets as it can. So if this situation persists for a longer period of time, I mean, if there is no one who can tell A and B that slow down, okay, you are causing problem for this router. If no one tells A and B to slow down, and A and B continues at 100 megabit per second, then this queue will eventually fill up, and what will happen? Then the router will have to drop the packet. So this is called loss. Okay, this is the situation which is called loss. Okay. Before going onward, one thing that is not mentioned on the slide, we can quantify queuing delay in terms of transmission delay. Okay, we can quantify queuing delay in terms of transmission delay. The formula for transmission delay was L by R. Okay, now if I pose you guys a question that, for example, in this figure right now there are, you know, right here, 1, 2, 3, and 4. There are 4 packets right now in the queue. Okay, and forget about the other 2 that are coming right here and right here. Forget about the other 2. Let's say there are 4 packets in the queue, and if I want to ask you how much queuing delay each packet will incur, how much queuing delay will be incurred on each packet, then can you quantify the amount of time the packet has to wait in the queue? Anyone? Can you quantify queuing delay? By the way, of all the delays in the internet, quantifying queuing delay is very hard. You know, calculating transmission delay is simple. You know, just like that, L by R. Calculating propagation delay is very simple. D by S. D is the distance, S is the speed of light in that medium, and distance divided by speed, you know, propagation delay. It's just like calculating the propagation delay of the car on the road. You divide the length of the road by the speed of the car, you will get the propagation delay. Okay, and the processing delay is usually negligible. And this is the 4th type of the delay, queuing delay. Quantifying this delay is very hard. There is no clear-cut formula for calculating the queuing delay, because you don't know how much, you know, you will have to wait, because it will keep changing all the time. Right now, during this transmission, we are talking in this MS Teams session, you know, at every instant of time, the state of the router is very different. Okay, you will have good quality of my speech depending upon wherever you are in the DL mod. Okay, now my question is, but still, if we want to, in this particular scenario, so I mean, we don't have a generic formula for queuing delay. We can't quantify it. But in this particular scenario, if I know that there are these 4 packets in the queue, if I ask you guys, can I calculate the queuing delay of these 4 packets? Is it possible? Can you do that?
Sir, I think the
You
size of the packet would have to be divided by the difference in the outgoing and incoming rates.
the size of the packet will be divided. I receive an answer in the DL mode. I'm repeating here for the FTF students. The size of the packet will be divided by the difference of incoming and outgoing. Well, this I don't know if it is right or not, but it is kind of very technical and maybe a bit confusing statement. But thank you for your answer. Um, let me put it in simple words. Forget about all these packets over here. Okay. Forget about these packets. Forget about this packet and this packet. These are just the 4 packets. I am just asking you. There are 4 packets. Okay. Let me give you a simple example. Okay. You walk into the bank and you are the first person. You are the first person. There is no one at the counter. How much queuing delay you will have? 0. You don't have to wait for your turn. You will go and you will be served immediately because there is no one in the queue. You walk into the bank and there is one person at the counter. How much queuing delay you will suffer? How much you have to wait for the queue in the queue? The amount of time it gets the first person to get served. In this scenario, now listen to me. The first packet, how much queuing delay it will have? 0. The second packet, how much it will have to wait? It will only have to wait the amount of time the router will take for the first packet to transmit, and the router will take L by R time to transmit the first packet. So for the first packet, the queuing delay is 0. For the second packet, the queuing delay is L by R. And for the third packet, the queuing delay is 2L by R. And if we assume that all packets are of equal length, if we assume that, and for the nth packet, the queuing delay is n minus 1 into L by R, right? Okay, so we can quantify queuing delay in terms of transmission delay. Okay, but at a particular scenario, I mean, if we know how many packets are in the queue, if there is a generic formula, no, there is not. Quantifying queuing delay with the generic formula, it's not possible. Okay, right. So then
Sir, I have a
let's.
question.
जी please. जी question
सर ये
please.
जो आपने
बताइए.
एग्जांपल दिए जिसके अंदर राउटर के अंदर एक क्यू बन रही है
Yes.
बिकॉज ऑफ डिफरेंस ऑफ ट्रांसमिशन रेट्स, तो अगर हम रियल लाइफ एग्जांपल में देखें, फॉर एग्जांपल हमारा ईथरनेट की जो कनेक्टिविटी होती है विद राउटर इट्स अराउंड 100 Mbps एंड द कनेक्टिविटी वी हैव नॉर्मली फॉर द DSL इज अराउंड 10 Mbps. तो उसके अंदर तो पैकेट लॉस में फेस नहीं हो रहा था व्हाइल वी आर अपलोडिंग एनी डाटा, तो वो कैसे अवॉइड होता है?
Okay. Again, thank you for your question, Ali Amjad. Absolutely right. I will repeat the question. The question is it's a good question, but it's a very simple one in the sense that it should come in everybody's mind. Okay, that usually the speed with which we are connected with the internet is 100 Mbps theoretical speed. Okay, theoretical. By the way, Ali Amjad, that is the theoretical speed. We usually don't get that much speed, but still you are right that the speed with which you are connected in your lab or right here in SEEX with the internet is usually very high compared to the backend speed which you get if at home the DSL speed, or if right here the backend that the NUST is having. Okay, then why we don't have too many losses? I mean, he says in his question that that we don't experience losses. Why is this the case? The reason is if this situation, now coming back to the slide, I will answer your question on this slide. If this situation persists and no one is here to tell A and B, okay, no one is here to tell A and B that you have to slow down because your rate is not appropriate for this router, then there will be many losses. But thankfully, we will study in our course that there is a protocol which is called TCP, Transmission Control Protocol, and that protocol, if running at node A and at node B, will ensure that these devices will transmit at their appropriate rate, the rate which network will sustain, and not the rate which will overburden the network. So the reason why we don't get losses is because at this end where I am transmitting, I am not transmitting right now 100 Mbps, although it is my theoretical speed, but there are protocols which are limiting my transmission. Okay, and they are making sure that this situation at the router do not persist for a very longer period of time, so that the queue will fill up and losses will happen. Okay, Ali, did I answer your question? So there are protocols
sir.
which will
Thank you.
make so TCP basically perform congestion control. We will study congestion control, not in detail, but we will touch congestion control 2 or 3 weeks down the line. Okay, in which we will
So
see
if there are
how
more than one router in the network, जो कि आपके for example within a couple of labs से होके या servers होके जाता है, एक से ज़्यादा routers हैं, तो will the TCP protocol be implemented on all the routers also, या सिर्फ A और B के ऊपर implemented होता है?
Okay, again I repeat the question. He's asking that if there are more routers during the way, then the TCP protocol will be implemented on all the routers. Firstly, the TCP protocol will not be implemented on any of the routers. TCP is a transmission control protocol. It's a transport layer protocol. The transport layer protocol only resides in the end system. Router is a layer 3 device. Router do not have any understanding of transport layer. So router don't understand TCP. Now, again, a question coming to our mind. The discussion is becoming a bit long with this question, that how TCP control congestion? I mean, if it do not seize the router, or if this protocol is not on the router, because we can clearly see in the example that only the router knows the congestion level. Now that's a magic that we will study, 2-3 weeks down the line, or maybe you guys have already studied in your UG courses, and we will have a brief recap of that. TCP maintain an end-to-end congestion control based on its own view of the network, and it will create its own view without any help. So we will study that right now, just because that's a proper separate topic of a whole week, maybe, right? Of 3 lectures.
ठीक है सर, आगे आ रहा है.
Okay, yes, it will come onwards. Right now, you can, the very quick answer of your question is that there are protocols which will ensure that congestion is controlled, and this situation do not persist for a longer period of time. Okay.
ठीक है सर.
Right. So in the next slide, we can see some of the benefits of using packet switching. Now we talked a lot about the problems that arise with packet switching. In the previous slides, we were talking about the new problems, new phenomena that will arise with the packet switching. So with the packet switching, we will have store and forward. With the packet switching, we will have queuing delay. With the packet switching, we might have losses. Okay. But then, I mean, if there are so many problems, then why packet switching? The answer lies in this slide and in the next slide, that the potential gain of packet switching is enormous when it comes to sharing of medium. Okay, so for example, in this small example, we can see that we have a link of 1 megabit per second right here. Okay, and we have n users, right? We have n users, and we want to, obviously these all n users will have their own separate link with the router, but in the end, the bandwidth that these n users will be sharing is this link, right? Okay, the bandwidth that these n users will be sharing will be this particular link, right? So now we will have to take into account how to divide this bandwidth among these n users, how to share this bandwidth. One way is circuit switching. Now let's look into some numbers. We have a link of 1 megabit per second, and each user require 100 kilobit per second when active. Now these are internet users, not the telephone user, not the circuit switch user. So they will be active, they will be inactive, just like us. Okay, sometimes we use internet, sometimes we don't. Bursty use, bursty nature, just like we studied few slides back. So each user will require 100 kilobit per second when active, and each user is active only 10% of the time. These are the numbers which we have been given. Okay. Now, if we use circuit switching, how many users we can accommodate? We have a link of 1 Mbps. We will simply divide 1 Mbps by 100 kbps, right? Okay. And we will get the answer 10. Because circuit switching don't care that if the users are active or not, if they and how much percent of the time they are active, right? Whether they are active 10% of the time, and the remaining 90% of the day they are not active, right? 10% of the time means out of 24 hours, 2.4 hours, right? And the rest, all 21.6 hours, they are not active, right? But circuit switching don't care, because it cannot take that into account. The way circuit switching divides the bandwidth is, equal chunks. So 1 Mbps, equal chunks of 100 kbps, right? That's the answer right here, 10 users. Now let's see if we can do better with packet switching and how packet switching does this division. But before that, I have a I have a chat. Can we have 10 minutes break? Yes, we will have a break. After, just let me conclude this slide, okay? Just let me conclude this slide, and then we'll have a break. Just let's have a look at these numbers, and then we will have this break. So I'm writing a statement here, okay, and then I will talk about how these numbers come. But I'm writing a statement. I'm saying that with packet switching, 35 users can be accommodated with the probability that greater than 10 users are active at the same time of 0.0004. Okay, so let me repeat. Another way of saying this statement is like that. The probability, I mean, I can accommodate 35 users, okay? I can accommodate 35 users with packet switching, and the probability that 10 users or less than 10 users are active at a particular time, that probability is 99.9996%, okay? And the remaining probability, 0.0004% probability, is that more than 10 users are active. You understand the statement or not? Confusing statement. Okay, let me repeat. Let me repeat. And if Abdullah don't mind, I will repeat this particular statement in Urdu and then in English as well. Okay. बात यहाँ पे ये हो रही है कि 35 यूजर्स में से 10 यूजर्स के एक्टिव होने की प्रोबेबिलिटी, 10 या 10 से कम यूजर्स के एक्टिव होने की प्रोबेबिलिटी 99.9996% है, ठीक है। और 10 से ज्यादा यूजर्स एक्टिव हो सकते हैं एक टाइम पे, उसकी प्रोबेबिलिटी सिर्फ 0.0004% है। अच्छा, हमारे लिए प्रॉब्लमेटिक सिचुएशन क्या है जब 10 से ज्यादा यूजर्स एक्टिव होंगे? क्योंकि अगर 10 से ज्यादा यूजर एक्टिव हों, हमने देखे ना, हमने 35 यूजर्स में शेयर कर दिए बैंडविड्थ, ओके, वी हैव शेयर्ड द बैंडविड्थ इन 35 यूजर्स, व्हिच इज वे मोर देन द नंबर that can be supported in circuit switching, right? Okay, but remember, internet designers, they always want to be greedy. I mean, not designers, but the business owners, right? The people who are, like, for example, in Pakistan, Neatel and PTCL, the people who are, you know, giving access to domestic and industrial users, the ISPs. Yes, thank you. The ISPs. The correct way of saying is the ISPs. They want to be greedy. Okay, they want to make sure that their resources are shared among as many numbers of users as possible, but maintaining a certain quality of service as well. And the quality of service is that whenever a user is active, he or she will get their desired share of bandwidth. So in this example, their desired share is 100 kbps. So what we want to do is, we want to accommodate as many users, but we want to make sure that out of those users, at the same time, only 10 or less than 10 are active. Because only 10 or less than 10 are active, then it's a circuit-like behavior. You understand that? You are doing packet switching, but the users are getting a circuit-like behavior. A circuit-like behavior is when you have guarantee of delay and throughput. Okay? Packet switching in packet switching, there is no guarantee of delay and throughput, but you want to achieve that. Okay? Now, where do we get these numbers? Okay? Just last thing, and then we will have a break. We get those numbers from this binomial distribution. Okay, we put our numbers in this, and it's a hit and trial case. Okay, it's a hit and trial case, and you have these figures in front of you, which I obtained from MATLAB. Okay, so you have a SMG calculator in MATLAB. You put your numbers in that. Let me explain. Over here, on the left side, you have a figure in which on the y-axis you have the probability that X users are active, and on the x-axis you have the number of users. Okay, and you are plotting for 35 users. Now just have a look. The probability that only one user is active, only one, is right here. This one. You understand? This is the probability that only one user is active. The second bar, this is the probability that two users are active at the same time. Okay, and this is the probability that 3 and 4 and 5 and 6 and 7 and 8, 9 and 10. And then these black dots, very little black dots, these are the probabilities of having more than 10 users active at the same time. And you can see that the probability of more than 24 users at the same time is not even possible. Okay, with these numbers, please note, these are the numbers which we are taking into account. Okay, and these numbers, where do these numbers fit in the formula? Okay, These numbers fit in the formula right here. Okay, the probability is 0.1, and 0.1, where do we get 0.1? We get 0.1 from here, 10% of the time. 10% means that the probability that the user is active is 0.1 of any particular user. Okay, so now if we put these numbers over here, we have n which is 35. Okay, we have x which is 10. We want 10 users to be active, right? We are interested in 10, right? So we want to calculate binomial distribution of 10 over 35, right? 10 over 35. So then the probability that 10 users are active multiplied by 1 minus p n minus x, which means all the remaining users are active. 35 minus 10, the remaining 25 users are active. And when we are not interested in solving the formula here, in solving the math here, but the point is this is what is being used to have this. We are interested in having an understanding of this, and if we sum up all these bars over here, we will get 99.9996. And if we sum up these black dots, then we will get 0.0004. Okay, and if the ISP gets a bit greedy and try to accommodate 70 users, then these are the numbers. And you can see that this is not very good. 0.91 means that throughout the day you can have 0.91 means that if you accommodate 70 users, you can see that there are the black bars are over here. They are getting a bit larger in size compared to this graph over here. So this is the ISP becoming a bit greedy, accommodating 70 users in the same bandwidth. So now the quality of service will not be maintained. Because why? Because the 0.91 means that the remaining 9% of the time we have more than 10 users active, and 9% is a significant amount of time throughout the day. 9% means that we will have a good portion of 2.5 hours throughout the day where people will suffer with too much congestion. They will not get their desired 100 kbps. So these are not good numbers, but this is good number. And if we compare with circuit switching, so we have 3.5 times gain. Circuit switching, we can accommodate 10 users. With packet switching, we are accommodating 35. So SMG, statistical multiplexing gain, is 3.5 times. Okay, I took more time. I'm sorry. I will stop the recording here. Let the meeting continue. Okay, let the meeting continue, and we will have a 10 minutes break. Okay, and then we will continue after the break. Right? Agree? Everyone? Okay. Agreement is more required from the people in the DL mode, because the total strength is over here.
ठीक है सर.
Yes sir.
All
agree. Ji, after it's 7:03 at my laptop's watch clock. So 12 minutes की break ले लेते हैं. We can have a break of 12 minutes and 7:15. Let's reconvene at 7:15. Okay. Okay, ji, I will stop recording over here, and but I'm here for the next 2 minutes to have any question from the DL mode. There are many students in the DL mode. If you have any question, please let me know. I'm stopping the recording so that